just in case. Okay, I'm recording now. Okay. Right, if you are comfortable with everything. Thank you. ¿Se vio? Sí. Is okay? Everything is okay?
Yes, yes.
C'est bien? Let me connect one thing. It's only connect also the chat. Vous avez ici le chat, ok? C'est bien.
You see it.
C'est bien. Environ. Let's see. Il est Ivan. Alors, il est confusion, non? C'est bien. Alors, parfait.
Hello, everyone. Welcome to the last lecture. Last lecture, talking about the introduction to coding theory over finite Frobenius local rim. You begin by some basic result of information theory. Information theory, talking about how to send the message via noisy channel. We have a noisy discrete symmetric channel with input and output alphabet R of design Q and of error probability P. When we send a word X into the noisy channel, we can receive X if the transmission is correct. They are received Y's y is different to x if there are an error. We have the transmission matrix. Transmission matrix is the matrix whose coefficients are the conditional probability. We have probability to receive y's given x is sent. P probability of receive y's given that x is sent is p minus is 1 minus p if y is equal x. In this case, we have the correct transmission. This probability is p over q1 if y is different to x. In this case, there are an error. Note that this transmission matrix is symmetric. Okay. Let pxy is be a transmission matrix of a discrete symmetric channel with input-output alphabet R of design Q with error probability P. The channel is discrete if the alphabet is discrete. In this case, our alphabet is finite. We have this communication system. Your objective is to send a message into noisy channel. When you send a message, the mechanism consists of two encoding this message. Encoding this message is at the redundancies bit. The left of the word become the length of the word the word obtained is greater than the length of the message. This word is called code word. Code word is sent into the noisy channel. The received word can be have the error. They are the decoding. Decoding consists to obtain the message is emitted. The channel is the memoryless if the probability to receive the word wise given the code word X is the product of conditional probability. This is important to establish the relationships between condition probability, matrix transmission, and random mean distance. Okay. The basic of the coding theory focus of focus on error correcting code for reliable data transmission. We have the message set. The message set is the final non-empty set. Denote the M is the possible message. We have the alphabet. Alphabet is the final non-empty set. Denote the R of the symbol. When cardinality of I equal 2, we talking about the binary channel. The element of this alphabet is 0 or 1. We have encoder. Encoder is the injective map to message set from message set to R power n. This injective map send any message to a unique code word. The code word is the same. The left code word in this case is n. Positive integer. It is a positive integer n. After, we have the noisy channel. The noisy channel, during the transmission, error may corrupt the code word into the different screen wise. Finally, when the code word is corrupt, has been corrupted during the transmission, decoding consists to determine the original message from corrupted to wise. We have this communication channel encoding, noisy channel, and decoding. Okay. Error correcting code. Error correcting code provide a ways to protect the message from corruption during message or storage. This is accomplished by adding redundancy in such a ways that with higher probability, the original message can be recovered from the received message. When we send when you send the code word into the noisy channel. Noisy channel is a discrete memoryless symmetric. The received word can be corrected. The decoder consists of determining the original message from the corrupted received word. Okay. An error correcting code is a structured way to introduce redundancy into data to detect and correct error caused by noising during transmission or storage formally consists of alphabet, message space, error correcting code. Error correcting code is the image of decoding. Decoding function is the injective map to message speech from message speech to R power n. Okay. Finally, we have decoding function. Decoding function is a function that maps a received word to a message or code word. The coding function consists to determine the original message from the received word. Parameters of error correcting codes. Parameters of error correcting code are first left, second cardinality, and first and last minimum handling distance. Minimum handling distance is the length of distance between different code, different word code, different word code. In this case, code word place. In this case, code word C and C prime must be different. A code C with minimum distance D can detect open to D-1 error. Since distance between C and Y is less than D-1 and C element of the correcting of the error correcting code, then Y does not belong to C. If Y belong to C, we have C and Y is two elements of C. In this case, a two element of C. In this case, we have minimal. We have distance between both word code of C is greater than D. D is the minimum distance. Donc, a objective to construct the error correcting code is the minimum distance must be a greatest. It's supposed to be a greatest. Okay. Donc, error correcting code detect up to D-1 error and correct up to D-1/2 errors. Other important quantity for an error correcting code C over an alphabet R with parameters left, that is n, cardinality, that is number of element of code, error correcting code, and D, minimum distance of code. We have the data rate of C. Data rate of C is the rate of logarithm in base cardinality of alphabet of cardinality of C over N. Relative distance of C is defined by minimum distance, minimum Hamming distance of C over left, that is A. Objective is both rate must be as large as possible. That is the objective to construction. That is the objective to construction of the error correcting code. Okay. Good error correcting code. A family of codes Cn with parameters n cardinality of Cn Dn over alphabet A, the same alphabet, is good in the Shannon sense if limit inf this data rate is different of 0. And limit if relative distance are different of 0. Limit when left become as large as possible. Finally, decodability. There exists an efficient decoding algorithm that corrects up to dn-1 over 2 errors with a probability of decoding error that vanish as n become as large as possible. Shannon foundation and size. Shannon theorem, Shannon noising channel coding theory state that for any discrete memoryless channel with capacity C, capacity of the channel expressed for capacity per channel is the function of entropy of the channel. Capacity with capacity C. We repeat, for any discrete memoryless channel with capacity C, there exists the good code in the Shannon sense. Code, a family of code is good if 1, 2, 3 are satisfied. If there exists good codes that allow the near perfect communication at any rate less than C, any rate R less than C, provide the code left is sufficiently late. We note that Shannon's proof is not constructive. It doesn't tell us how to designs such good codes or decoders. Practical coding theory focus on linear code with offer an algebraic structure that allows encoding, decoding. Okay. We can say that the consequence the coding theory is a consequence of information theory. The coding theory is a consequence, is the sub theory of the information theory. Okay, Shannon state a noisy channel coding theory. Ramnin state the practical construction of error correcting code and propose Shannon is the pioneer to propose a error correcting code and their decoding. This code where the name and so called it and is called Ramnin code. Shannon state this theorem in 1949, and Richard Shannon gave a practical contribution in 1915. In 1915, Richard Shannon brings information theory and practical coding by inventing the first error correcting code, Ramnin codes. It defines a Ramnin distance and provide the constructive code design framework that Shannon's existence prove latex. Okay. We're talking about the maximum likelihood decoding. Maximum likelihood decoding works when you use the noisy discrete symmetric Merolis channel with the same alphabet input output A versus or C, of cardinality Q of error probability P and error correcting code C over A of left N encodes broadcasting message. We search for the code word C that maximize the probability. Okay. C is a code word that send into the channel you receive twice. When the probability to receive twice given code word C is maximal, we can decode it C we can decode it twice by C. That is in this maximum likelihood decoding. With this 2, 3, and 4. Since channel is memorized, we can use okay. Channels is memorized, we have equality. This probability is the product of condition probability. Okay, we use the condition of memoryless of this channel. Okay, you continuous equality free. You separate these products to 2 products. First product, we have error. We have error at the time I x to I is different to y's I. The probability of receive y's I given that xy is sent. This condition probability is P. P is the probability. P is the error probability of the channel. Is P. This product has distance of happening between C and Y's quantities. We have P power happening distance between C and Y's. Second product, in this case, there are no error. A probability we obtained we receive a message we receive a message they receive the code, they receive the word that doesn't corrupted is 1 minus P. We have this we have express probability to receive a word twice, given that x is sent is P power distance on the happening between C and Y's dot 1 minus P power n minus distance of happening between S and Y's. This happening distance between 2 words expressed defined by this is the number of I between 1 and n such that xi different to y's I. Okay. This equality we can say that if probability of y's given C is maximized, this is equivalent to distance of happening between C and Y is small. Maximal, c'est probability is equivalent to minimize to distance of happening. Donc, decoding the maximum likely one decoding is determined of what is close to the what is the close to the code word. Okay. Donc, each errors bit contributes a probability error factor of P, and each correct bit contribute minus 1 minus P. If probability error less than 1/2, we observe that maximize this conditional probability equivalent to minimize this Hamilton distance between C and Y. For a binary symmetry channel with crossover probability P less than 1/2, maximum linked rule decoding is equivalent to choose to code word C that is closest in Hamilton distance to the received word twice. We have this example. C is the Hamilton distance. Pardon, C is the Hamilton code. C have the 16 code word. 16 code word. First, we have the message. 16 message. The left of message is 4. Each message has 4 bits. We encoding each message, we have code words. We send each code words into the kernel. We receive word-wise. For example, if you receive word 1101110, which message can be, which code word can be corrected to receive this message. We compute the Hamilton distance between this receive word with the code word. With determine the Hamilton distance, we obtained uh, we obtained okay, this distance between this word code and this is 1. Donc, this code word is close to this. We decoding this receive code by this code. Donc, probably the code word that is sent is 1100,110. Okay. Linear code over final ring is and is dual. Let R be a final ring. A linear code over alphabet R of left n is the submodule of R power n. Into ambient space R power n, we attach a Euclidean interproduct. The joule of C with respect to his interproduct is the set of element of Rn that is Euclidean interproduct is 0. That is Euclidean interproduct of V with any code work in C equals 0. The joule of C is a linear code. The joule of C is a linear code. The joule of C equals C. Okay, an application of joule. The 10-digit ISBN number, we see that the books, the 10-digit is a 10 number. This 10 number is called a 10-digit. The 10 ISBN. Okay. This code is correct if interproduct with word V is 1 2 dash 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 10. This word belongs to this field power 10. Field F11. 11 is the prima number. 11 is the final field with we have 11 elements. We compute the interproduct. If interproduct module 11 is 0, C is the ISNB code. We verify this example. We have W 81752576660. We compute, we obtain 0. Now this code is valid. Okay, example 2, application of joule in to verify this code. Here is the other code. The technique to verify this is correct. This is correct code. Okay. Well, we take other is an EISBN code. You verify this is the valid. Okay. You continue with the minimal generating set for a linear code. If a linear code over field, the linear generating set is the basis. When the code is the final string, the notion of basic is is not the same. It's not the same. Okay, we define the basis of the linear code over finary as minimal generality set and modular modular independencies. Okay. The minimal generality set is the generality set that is minimal, that is the cardinality in minimal. Definition, the set V1 V dash 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 Vk is the minimal generality set for C if C is generated by Vi, and for any generality set for C, the cardinality is greater than K. K is the number of the minimal generality sets. You know that any minimal generality sets have the same cardinality, and that cardinality is called the rank of C. It denotes that RK of C. Okay, when the ring is the field, the rank of C is the dimension. Okay. Basis for a code. Basis of a code. Let R be a final local ring with maximal integer R. Si a linear code over R of let n and V1 dash dash Vk is non-zero code word in C, we observe that, okay, we explain that there is the table that is important. In the vector space E is a K vector space. Okay, we have for any x a dans I times K. A égale if and only if A égale 0 of K or X égale 0 of E. When M is an R module, this relation, okay, this relation becomes M becomes A égale 0 of R or X égale, sorry. Okay. This is important. Okay. In this case, X belong to M, A belong to E. Yes, A belong to annihilator over R of X. We call that annihilator of X is a element, is the set of is the set. It's the set. Okay. It's the set of elements of R such that X equal cell of R. Okay. That is annihilator. Annihilator is the integer of R. It's the integer of R. Okay. Annihilator. So, annihilator. Okay. Annihilator is content of the maximal integer. Okay. Of the maximal integer. This we have equivalence. We know that K is the field. K is the field. The maximal integer of K is singleton 0. The only integer of the field is singleton 0 phi is same. Is self. In this case, we have okay. Okay. Donc, so that this equivalence allowed me to say that linear independence implies modular independence. Okay. Vectors, the vectors v1 dash 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 vk is modular independence if for all alpha 1 dash 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 alpha k in R, if this sum is 0, then all alpha e is the element of the integer, of the maximal integer. When v1 dash 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 vk is linear independence, if is the modular independent with annihilator of VA is singleton 0 for all I. The set is the basis for C. The set VI V2 dash dash VK is the basis for C. For of if is a generative set and modular independence is the both concept of concept. Generative set and modular independence. Okay. You know that the basis is the minimal generative sets, but inverse is not true. We see that in an indices. You know that the basis of C is the minimal generative sets. Do you have minimal generative sets implies modular independence? I think that is the answer is no. It's no. It's no. Okay. The generative set, the generator matrix for a linear code. The generator matrix of the linear code is the matrix whose roots form a R basis for C. A basis of 3 if the element in this basis is the linearly independent. We say that the basis is free. A code a code is called free. Parity check matrix for C is the matrix of the Joule. If J is the generator matrix for C, PG, where P is the inversible matrix, PG is also the generator matrix of D. The number of rows of the generator matrix is the rank of the linear codes. Okay. Free codes. We have this characteristic of the free code. C is the free code if and only if the generator matrix became put in this form, and parity matrix became put in this form. And C is a free. C is if and only if its Joule is also free. For example, of okay. Other characterization of the free code. C is free code. Is a free code. And rank of C is K. C is the free code over R. This meant that C is isomorphic to this. Okay, for example, and take R equal Z4, generator matrix, K equal free, generator matrix, we take D. Donc, identity matrix. Add when you want, you put free 0 2 0 2 free 1. Okay. This code, the left of this code is 6 7 7 7. The left of this code is 7. Okay. We note that this is the identity matrix. K is free, identity matrix. Okay. To second characterization of C, D is equal to identity matrix. K0 is rank of D. U is the permutation matrix. Encoding of free code over chain ring this is the crew when ring is when for any final ring. This is the crew. Is here R is the final local ring. G a generator matrix of the free code. We know that G can be put in this form. The encoder is the injective math. This function is injective. The image in this function is the error correction code. The cardinality of error correction code is cardinality of alphabet power k. K is the left of message. The left of message. Okay. When linear code is non-free, we take the final chain ring with l'importance and this less than 2. Less than 2. The general matrix and parity matrix can be put in this form. Can be put in this form. Okay. We know that we have K0, K1. This is the free part of code, of linear code C. Donc, K0 is the number of free roots of the matrix, and K1 is the number of root non-linear. From this G can be obtained the parity check matrix. The both matrix is put in the standard form. Okay. The couple K0, K1 is called the type of C. The type of C. When the type of C is allow us to determine the cardinality of C and rank of C. The type of C is couples K0, K1. The rank of C is K0 plus K1. And cardinality of C can be expressed as follows. Type of C is coupled K0, K1, type of C. The cardinal alphabet R is the final chain ring. Residue field FQ is the residue field of R. C is the linear code of let R of type K0, K1. Cardinality of C equal Q power 2K0 plus K1. 2K0 plus K1. This is the method to compute the cardinality of C when we know its type. Okay, it thus continues. Encode function for the non-free linear code. The set of message is this product. The set of this code, this product. Okay, D, a given byte. K0 is the number of the free roots and K1 is the number of non-free root of the generator matrix D. Okay, we obtained this encoder for C. Okay. Since encoder is injective function, the cardinality of C equal cardinality of set of message. Okay. For example, this is an example of the linear code of over Z4. K0, the type is 1, 2. There are one free root. There are two non-free roots. Okay. The cardinality of C is Z4. The residual field of Z4 is F2. Here, Q is 2. The cardinality of C is 2 power. Okay, and compute this. Okay. In this example, your tap copper is coupled 1, 2. Q equal to the cardinality of this code is 2 times 1 plus 2. Okay. 2 power 4, 16. Okay. And set of message is given by Z4 times this set power 2. We can see that the number of elements of Z4 is 4. The number element of this set of 4. 4 times 4 is 16. We count this 1, 2, 3, 4, 5, 6, 7, 8, 16. This is a code word of C. C has 16 code words. It's important to determine to compute a set of message. In this set of message, important to note how to compute this. Okay, continuous. Cycle code over final chain ring. We take the chain ring with an important indice 2. Important indice 2. The chain ring with important indice 2 the chain ring important indice 2 is isomorphic to okay. R is a final chain ring of maximal integer MR with nilpotence index Q if and only if R is a Galois ring. I is the P square M P square. This nilpotent is 2. Is the FQX x square. Nilpotence index 2. Okay. Okay. I think that this okay. Okay. No. If R is the financial ring and this of maximum there in these two, this R is isomorphic to Galois ring of characteristics P square, or R is isomorphic to this. This you can write FQ U, where U square equals 0. A U different. Okay. No. When you say final finishing ring of maximum integer with nilpotent index 2, we talking about this buff ring. Okay. The linear code C over R of left n if cycle code is cycle code if cyclic shifts of C is content of C. Cyclic shift defined by this equality. If we take the word, when it shift, we obtain the word C0 dash 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 Cn minus 2 Cn minus 1. We shift, we obtain the Cn minus 1 C0 dash 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 Cn minus 1. Okay. Theorem. C is circle if and only if the polynomial representation of C is an integer of Rn. Okay, this theorem allows us to identify cycle code with a integer of this ring. In the coding theorem, when code is a circle, we work with integers. Okay, we have these applications. The injection. Okay. C0 dash 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 C minus 1 send some CI power E, I go to 0, goes 0 from to n minus 1 plus this integer. When you note x bar, Rn can be right. Okay. C is circle. C is circle if and only if phi of C is integer of this ring. This ring is an principal integer. Any integer of this is any integer of this range is principal. This map phi is an R module isomorphism. Is R module phi is R module isomorphism. This R module isomorphism allows us to identify circle code with integers of this ring. In the circle, when you use circle code is this circle code is an integer of the principal integer in Rn. Okay. The principal questions is what are the generator? What are the generative sets of the circle code? This answer, the answer of these questions is given by when R is the local ring. When R is the local ring. First, well, become circle code is free circle code. When circle code is free, the generator the generator set of this code is the monic divisor of x power n minus 1. Donc, the circle code of let n is free if there exists a monic divisor d of x power n minus 1 in Rx such that d is generated by d. D is called the generator polynomial. And rank of the circle code equal n minus degree of d. The generator polynomial of joule of C is called parity check polynomial. So, if G is the generator polynomial of C, the generator polynomial of joule is H star. H star is definite is computed by GH is a point is x power n minus 1, and J star is I correct this. Okay, we write is a free circle code. In this case, C is generated by D. D is the demonic divisor of n, free code of left n. Other condition Left N and Q are copram. Q is the cardinality of residual field of R. R is a finite chain ring. Residual field of R. Okay. The generator matrix of Joule H star, where H, GH, and H star equal X power degree of H. In the lecture, we call it H star a reciprocal. H star is called it reciprocal polynomial of H. Okay. For example, you give n equal 8, q equal 3. In Z9, we have use a Hellsel lift to obtain these decompositions. Use a Hellsel lift. I think that is 5 here. Okay. You take this, this is 8. C is D, and Joule de C is a Joule, is a reciprocal polynomial is okay. Reciprocal polynomial. You have this property, if A, and use this here, you'll be 8x squared plus 4 plus 1. 8x squared plus 5 plus 1. Oh, we want this polynomial must be a monic, must be two monic. Is R is Z9. In Z9, 8 times 8 equal 1. Okay, when you express this polynomial, you obtained a monic polynomial. Okay. This is the mechanism to construct the free circle code. How many free circle code are there? How many free circle code are there? You take this example, you compute D is the modic divisor of here is 8, is 8. 8. Okay. This is enough to compute the number of the divisor of the divisor of 8 of x power 8 minus 1. S power 8 minus 1 has 1, 2, 3, 4, 5. 5 monic irreducible polynomial. The number of the monic divisor of x power 8 minus 1 is 2 power 5. 5 is the number of the monic irreducible polynomial over most individual in this into factorization of this polynomial. Okay. Donc there are 2 power 5 free circle code. 2 power 5 free circle code can be constructed of left no. Donc there are 13 2 free circle 6 there are free circle cyclic code over Z9 of left 8. Okay. Encoding with a free of the free circles of the free circle cyclic code over finite chain ring. In this case, this chain ring, okay, in this we can replace finite chain ring by finite local ring. The result obtained is satisfied. Okay. The message, you take a message, you transform this message and polynomial and compute this product x overline x equal x plus integral. Okay. Donc to encoding, we take the message and transform okay. We take this example to explain that. And okay, I take a key free Z9 power free Z9 power 8. Okay, this message here MI I02 plus G modulo we have is not steering Z9X. Okay. We compute modulo X power 8 minus 1. Okay, this the encoder with free circle code. Non-free circle code, we distinguish two cases. First case, C is generated by theta D. Theta is the generator of maximal integer of R, and D is the monic divisor of the x power n minus 1. The encode, I forgot theta. I forgot theta. The set of matrix things in this R is the chain ring. Here the set of message K is the R power K. Here is the Teschnuller set power K. I forgot theta. I forgot theta. No. I forgot theta. Teschnuller power K. Rx. Okay. M associate mx. Mx is polynomial representation, polynomial representation of a message M. D x. I forgot theta here. Theta, forgot theta here. Modulo. We compute modulo x. Okay. This x bar, j bar, ou x bar x equal x plus this integer. Okay. This in this case, C is generated by theta t. Où j bar is the monic divisor of this polynomial. You use Rel-Lift to factorize this polynomial into the basic irreducible polynomial. Okay, second, C is generated by Fj theta Fh, where Fj égale x power n minus 1. Fj harmonic. The encoder is defined by this map. In this, you have set of message in this product of set. A belong to k power k, R power k0, and B belong to Teschner set power k1. Here is a k1. It's not k0, k1. Associate this sum. Okay. The type of the code is k0, k1. Okay, the type of the code is k0, k1. Okay. You continue with the harmony 8. The harmony 8 can be expressed from the harmony distance. The harmony distance. Okay. How many width how many width of the word? X is the distance of this word to 0. From the linear code C, we can construct the circle of this code and quotient of this code. The circle of this code is the set of all elements of this code verify theta C equals 0. The quotient of the code of the set of the word belongs to R power n such that the theta C belongs to C. Note that the linear code C is the subset of its quotient and contains the circle. The quotient of C is always free codes. It's important to note that the width, the remaining width or distance or remaining distance between the remaining width of the linear code equal the remaining distance of the code. This equality is satisfied if code is linear. It's important to note that the remaining width of the code is equal to remaining width of the circle. Is equal to the remaining width of the quotient. That is important. It's important. Continues with the MacWilliams identities for the remaining width of the code. Remaining width of the code is the minimal, is the smallest, is the smallest remaining width of the non-zero code. Okay. The remaining width enumerator of C is defined by this equality. MacWilliams identity related remaining width enumerator of C with its joule. This MacWilliams identity is satisfied if the ring is the Frobenius. You have identity 7. Identity 7. No. Identity 7 is called the MacWilliams identity. When is no remaining width enumerator of C, you use the MacWilliams identity to compute the remaining width enumerator of the joule, of his joule. Okay, that is example. You use the linear code of generator matrix J. This is the word code. This is the word code. We know that there are one word code of remaining width 0. This code width, the remaining width is 0. Here the remaining width is 2, 2, 2, 4, 4, 4, 4. 4, 2, 2, 2, 4, 4, 4, 4. We count. In Y's power 4, the coefficient is 1. This means there are one word code with harmony with 1. We see the exponent of Y's. The exponent of Y's is here is 2. The coefficient is 6. This means that there are 6 word code which with this which harmony with 2. There are 6. Here we count this code word 1, 2, 3, 4, 5, 6. Et other 8 is the harmony with the other word codes. They are the harmony with other word code is 4. There are 9 word codes which harmony with 4. We count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay, you try to use the such math. You try to use this. Where is this program? Enumerator. Okay. 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 C'est bon. This is good. Okay. This is the program to compute. Okay. Here you put the generator matrix. You put here. Okay. You compute. Okay. Then you obtained. Here is X is Y in this course. A Y we remplace by 1. We see that there are one code word is harmony with 0. There are 6 code word they harmony with 2. There are 9 code word they harmony with 4. Okay. Donc after this course, send me the mail. You send this program. This is important to PhD students to help me this program to alone to help me to know the minimal harming distance. In this year, the minimal harming distance is 2. Is 2. Is 2. Okay. This program work for the linear code over finite chain ring over finite chain ring. Okay. This program works for any linear code over. You use this. You use this. You use this. The use this. Okay. P becomes change. You take 2. We take free. 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 Well, okay. This is the generator. This is the Hamlin 8 enumerator for linear code over Z9 with generator matrix here. Okay. Bon, it continues. Not important to know the MacWilliams identity is valid if the ring is the ring is the Frobenius ring. Okay. For example of linear code over Z4, we take the same example. The circle we devise any road. The circle of quotient. Quotient is the set of the word that theta C is belong to C. And circle is set of element of C such that theta C equals 0. Okay, this example, we devise the non-free routes by 2. Z4, the generator of maximum integer is 2. We divide obtained 1, 1, 1, 1, 0, 1 is here 1, 1, 1. This code is free. Circle, we multiply the free roads by 2. There are one free road first. 1, 1, 1 multiplied by 2, obtain 2, 2, 2, 2, 2. Okay. This code is non-free. Here is free. C, the code C, the free code C, circle of C, of quotient of C, has the same Hamlin has the same minimal Hamlin distance. And this minimal Hamlin distance is 2. Is 2. Okay. Evaluate the performance of this free code. We return of top. Okay. Data rate and relative rate. For the code, we objective to make this buff rate of late as late as possible. And code of optimal if these quantities are late. Okay. We compute the data rate and relative rate of the C of a code C is circle of quotient and compare. Okay, we return. Okay, we return that compute. We go to bar. We go to bar. The parameter of C let is 4. Cardinality of C is 16. Distance is 2. Okay. Second, the same cardinality for circle of C compute. Minimum rounding distance is 2. Here 4 quotient of C compute 2. This code is free. This code is free. How to compute the cardinality. You return. Okay. Free code. The free code. Okay. When his code is free, the cardinality is equal cardinality of alphabet power k. K is the rank of the code. Here, the rank of this code is free. The cardinality of this free code is cardinality of alphabet that is 4 power free. 4 power free. 4 power free. Here, circle. Circle is the non-free. It's important to know the type of circle. The type of circle, all rows of the generator matrix of the circle is non-free. So the type of circle is the 0 free. It's a couple 0 free. The type of circle the type of circle K0, K1, 0 free. Donc, in this case, the course say that cardinality. Okay, is here. Cardinality is 2K0 plus K1. We use that to compute. Use that to compute 0 times 2 plus 3. 2 power 3. Okay, you compute the rate rate so rate okay, data rate, oui, data rate compute en relative distance. Ok, data rate c'est route C et delta C. Ok, je colle data route of C is log in base A of over N. Here A is A. A is Z4. Cardinality of A is 4. Compute log in base of 6 is 2. Here rate of C 2 over 4. Relative distance of C 2 over 4. Here is we circle. Donc c'était plus ici here. 8 et we compute log for 8. Log for et 2. That is yes. Okay. Data rate of circle of C égale 3 over 2 over 4. 3 over A. Okay, we can erase this. Here, a data, the rate of the relative rate of the circle is the same. Here, you compute 4. 4 2 power 6. 6 2 3. The data rate of quotient of C is okay. You can we note that okay, we know that here data rate is here and here. Okay, we compare this. The smallest data days is this. After here, and this code is free. This code is free. We have these conclusions of this remark. Conclusion of this remark. Okay, Running distance. The best linear code are free. When you use running distance, is it better to use the free code to construct the optimal linear code. In this case, the quotient code that is free is optimal with respect to linear code C and circle of code C. Okay, this remark belongs to researchers in coding theory to propose the order metric, the order 8. For example, the order 8, we have the Lie 8, the homogeneous 8. In this course, we talking about the Lie 8 over Z4. The Lie 8 over Z4 is defined by if x equals 0, the Lie 8 is 0. Is x equal 2, the Lie 8 is 2. This s is equal 1 or 3, the Lie is 1. This Lie 8 over Z4 can be extended to Z4 power n as follows. The Lie 8 of this word is the sum of Lie 8 of the comportment. And by width, the Lie 8 and define the Lie distance. The Lie distance are defined of the difference of the Lie 8 of difference of x minus y. Is the distance on Z4 power n. In 1994, Paris Soulet and Calvet-Ball used this metric to prove that the K-dot code, the prepare code, is a great image of linear code over Z4. K-dot code is constructed by use the class code Galois, is class map over Galois extension. This construction of the K-dot code is technical. We can advise to read this construction of K-dot code. We note the time to study this construction. Is the nice construction. Okay. We define the Lie 8. For example, we take the Verset example. Here you use the Hamlin 8. This you use 8. You remark that the free here the 8, the Lie 8 of this free code is 2. But the Lie 8 of C equal the Lie 8 of circle equal 2. In Lie distance, the best linear code can be non-free. when you use the non-free linear code, it's important to use the Lie width or homogeneous width. Okay. The gray map, we define the gray map of Z4 and extend that of Z4 power n. The gray map is the nonlinear isometric. The gray map establish isometry between Ramnin this is they are yeah yeah they are they are Ramnin width. Ramnin width, we finish by Ramnin width. We finish this course by Ramnin width. By gray map. Gray map establish bon, this example, this Ramnin distance here is 2n. This is n. Here Ramnin Lie. Okay. This is non-linear map and isometry. Okay, isometry. This okay. Ramnin distance between okay, isometric means that Lie distance de phi wise égale Ramnin distance of x. Ramnin distance between x of y's égale Lie distance between their image. Okay. Donc, this called gray map. Gray map is where generalized to any financial ring. The gray map where generalized to any financial ring. Okay. Okay. To finish this lecture too, we can say that the final ring R is acceptable in algebra according to ring only if it satisfies the MacWilliams identity. Means that R is a Frobenius ring. R is the Frobenius ring. Okay. Thank you a lot for kind attentions. This lessons, this course is finished today. If you have a question, you can write by email. This email, recall that is Alexandre FOTUE @gmail.com. You send the program, the search program to compute. Okay, thank you so much. See you one day. Okay, thank you.